First of all, Vladimir, thank you very much for the invitation to present the PLC-Easy solution, and nice to meet everybody from this end of the world. I'll quickly introduce myself. Martin Hilbers. I'm originally from the Netherlands. That's where I grew up and where I was educated. I started my career in industrial controls in 1998 in heavy industry, in steel and in paper, predominantly in an operation support, and then later on in a system integration role. Really got the touch on changing existing control systems, and of course with the background of an operation mindset behind there. Then in 2005, I immigrated to Australia, and in Australia, I got involved in the mining industry, so large greenfield, sometimes brownfield, so new and extension on existing mine sites. And with mining, especially in the precious metals, I did quite some gold. It's speed. You want to get that machine, that mine site operational as quick as you can. So what I found is that you do a lot of work where you generate software for your PLC or for your DCS. And I noticed throughout my roles that I was running into to very similar challenges, whether that was in operation, whether that was in system integration, or whether that was in large projects. And at that point, that was roughly 2010. At that point, I worked with PLC-SCADA, industrial controllers with a human machine interface on top, and with DCSs, distributed control system, and hybrid DCSs. And I noticed these challenges across those systems and across industries and across roles. And so I wasn't too familiar with the standards S88, S106, S18.2, and now IEC 61499. But I needed something that was simpler. I could clearly see that the way we program, we don't question it. This is the way we do it because we always done it that way. That was kind of the mindset that I was seeing. So in the mining industry, most of the mine sites are quite remote. It's not that you step in your car and you drive to a mine site. A lot of mine sites were in Africa. So I lived in Perth, Australia. So you have to fly to usually to South Africa, then you have an internal flight, and then you have a drive. And usually it takes 2 to 3 days to get to a mine site. So it's not that you travel home often. You go on a roster of 6 weeks or 8 weeks on, and then 2 weeks off. And what the issue is that I had is once the mine site was up and running and I left, a lot of times I would be called back like, hey, can you help us out? Because it was difficult to understand. In control systems, it's still a high level of expertise that you need. So I had a need for something that A, was quick, and B, was simple to understand. And that's when my ideas, I put some ideas into practical solutions, and that became PLC-Easy. Now, PLC-Easy is not a code generator, so it's not a program that you run in a PC that generates a PLC program. It's just very simple. It's a library, a very simplified library that makes use of a different architecture. So it's roughly what you could say it is a DCS solution within a PLC-SCADA environment. So you get the advantages of a DCS, that structure, that rigidity, that repeatability, but without the complexity of a DCS and without the vendor locking. Because a lot of times, if you buy a DCS, you can only make it work with the components of that manufacturer. So you get the advantage of a DCS with the advantages of a PLC, but without the complexity. So the verb keep it simple, stupid is basically the red line in PLC-Easy. Now, when I noticed the challenges that I had predominantly stemmed from two sources. So the complexity around providing an operator with accurate information and the complexity in the PLC code. Now, starting with the first one, if you look at a software architecture in a DCS or a PLC, you often see a sort of layered software architecture where at the bottom layer here, you see your standard software modules. So those are software modules that read and control your field components. So that could be a valve, a pump, an analog, a PID loop. And based on top of that, for instance, you have a sequencer or a group controller, or you have a routing functionality or batching functionality or clean in place. Now, in order to have these software modules work properly together, you make them interact with conditions, and you write down those interactions in your design document. And so you have a whole lot of these interactions that you need to contemplate. Now, a lot of times what happened is that during your design phase, you cannot predict all the situations that can occur in a real situation. And you're confronted with that in an operation environment. Once it's commissioned and it's running, it's in your factory, then you find out in a certain circumstance that your functionality doesn't work. And of course, you've got production pressure, and the person that needs to fix that is not going to go through a stack of design document, but that person is just going to put a fix in, right? And sooner or later, you will see that that fix has a side effect. So you put a fix on a fix. And before you know it, you see all these little software modifications that are not really coherent to start to appear in your software. And that's when you start to be confronted that your design doesn't match what you have in your PLC or in your DCS system anymore. And that really bites you when you want to add extra functionality. And because that becomes then very, very difficult. Now, in the PLC-Easy solution, what I did is I looked at those functionalities, those common functionalities that you find in most of the controls that you have in every process, so sequencing, routing, redundancy, etc. And I incorporated those functionality in the bottom layer, in the standard logic. So a valve is self-sequencing, is self-redundancy managing, is self-routing, is self-batching. And what you do to create your application, you link those software modules together. So instead of having all this software scaffolding around your standard logic software modules, so your pump control, your valve control, your analogs, you only have those software modules, those standard software modules. You only have your pump functionality and your analog and your valve. So you really dumb down, you simplify your software just to your standard logic. So if you look at your P&ID, you pretty much see 80% of your software. Now, to elaborate on that, if you consider a PLC or a DCS application as a pyramid, then you can roughly divide that pyramid up in 3 layers. Now, at the bottom, you've got that standard logic. So the software that controls your field devices or read your field devices, so your PID loops, analogs, digitals, your valves, your pumps, etc. In the best case scenario, that software takes about up 50% of your complete application. Now, the middle layer software contains the functionality that uniquely defines your process. So that's your sequencing, that's your routing, that's your group control. That really defines this is a dairy process, or this is a mining process, or this is a chemical process. And the third layer, the top layer of software, is software that supports the 2 bottom layers. So that could be communication handling, calculations, data configuration, have pretty much anything to facilitate those 2 software layers underneath it. Now, the bottom layer is completely standard. It's just a software module that you can apply in a dairy process or in a mining process. A valve is a valve, a pump is a pump. So that's standard. It's tested, done. The middle layer is unique. That's completely built for your particular process that you want to control. And the top layer is a mix of unique software and standard software. Now, from a complexity point of view, where you have unique software is where you have complexity. That's where the challenges for your engineer is, and that's where the challenges are once it's operational for the operator or for the maintenance people. So from a complexity point of view, you can say that the middle layer is roughly 60% of your complexity, and the top layer is about 40% of your complexity. Now, in the PLC-Easy solution, that middle layer is embedded in your bottom layer. So theoretically, you got 30% less software, and that's a very conservative estimate. In reality, it's more. Usually that middle layer is bigger. So 30% less software means 30% less design, less development, but best of all, it's 30% less software that's going to break on you in the middle of the night because it just doesn't exist. It's not going to malfunction on you. So the reliability of a simplified architecture and simplified software application is just higher. So you achieve a higher level of automation, a higher level of reliability. Now, in essence, what it is, it's a control algorithm. And the control algorithm contains all those common functionalities that you see in most of your process control applications. So routing, clean in place, alarm management. Now, all those functionalities that create complexity is embedded in that control algorithm. And that control algorithm is part of every function block in the library. So when you work with PLC-Easy, it's a collection of software modules, function blocks, and they all contain the same algorithm. And that makes it very easy because that algorithm only has 8 parameters. So whatever you do, you just program with 8 parameters. Now, if you compare that to another system, say for instance, Siemens PCS7 or Emerson Delta V, you find in their pre-configured software modules, their function block, that you find you have over 300 parameters. And every parameter has their specific functionality. Now, in PLC-Easy, it's only 8. So the learning curve is much shorter. It's much quicker to learn. Now, as I said, that makes things very easy because if you compare it with a Lego brick, and on the left-hand side here, you see the S88 physical model. So if you start at your bottom layer of that model, those are your control modules. So that could be valves, analogs, pumps, hey, you name it, something that's physical in your field, a control module. If you have a PLC-Easy software block, and I represent it here with a Lego brick, you have 8 parameters, and all what you do is you link those software modules together through those 8 parameters. Now, for instance, here I got a gas valve, and I want to have a redundant gas valve. And I want to group that with a steam valve, for instance. So all what I do is I link those 8 parameters of those blocks together, just like a standard Lego brick has 8 stubs where you click it together. You just link those software modules together, and now they perform a group functionality. And I can make that group as big as I want, right? It's literally like Lego. You just click them together. And I can sequence that with 2 other valves. And now I've got a group that's sequenced with 2 other valves. Now, from an object-oriented point of view and from an S88 standpoint, if I now would put an equipment module on top, and that's a software module in the library with the same 8 parameters, I just link it on top of that group. And all these colorful Lego bricks, all these function blocks at the control module level are now encapsulated in that equipment module. So it will follow whatever the equipment module will do. So if I have a standby equipment module, then all these colorful Lego bricks, all those function modules that are encapsulated in it will go to standby. Or if it's part of a sequence and you activate the equipment module, all the encapsulated control module that are underneath in a hierarchical way will just follow in that sequence. Now, redundancy is quite a common thing, especially in mine sites. A mine site is usually not conveniently located under a high power line. You have to provide your own generators. And there's a lot of redundancy in that. You want to keep that up. So in MindSight, you have a lot of redundant functionality. If the one functionality that controls, for instance, a pump, if the pump fails, you want the functionality of the other pump that controls the other pump, you want to have that kick in, right? So creating redundant functionality to program that for 2 modules is quite simple. But if it's, for instance, 2 pumps, of one runs at 100% and the other one is regulated for your flow need, and you have a third one that's in a standby, if one of the 2 pumps fail, the other one kicks in, now all of a sudden it becomes more complex. And the part of complexity is not so much in the functionality, but also in providing the operator with accurate information on your standby status, because there's nothing as dangerous as that you're under the impression that you have a standby module, and when you need it, it turns out it's not ready, right? It's like flying in an airplane at 10 kilometers high and your primary system fail, and then you find out that your secondary system is not available, and that's very dangerous. So within PLC-Easy, as soon as these blocks are linked, they not only provide the redundant functionality, but they instantly provide the information to the operator on the status of your duty standby configuration. Now, as I said, that is not limited to a single, it's infinite. So you can put any sort of device on you can have 5, 10, 100, 1,000 devices in duty standby if you want to, in any configuration. Now, the way you program at the control module level is the way you program at the equipment module level. So if I group this equipment module with another equipment module, I just link it through those 8 parameters. And on a unit level, same thing, same 8 parameters. I just click it on top. And now I've got a group that contains a unit, equipment module, and control module. And at a process cell level, same thing over and over again. You just program with those 8 parameters. And even at a process cell level, so in theory, I could have a whole factory in redundant. And if the smallest component in that redundancy setup is not ready to assume duty, the operator is automatically notified instantaneously. Now, in Lego bricks representation, this gives you a very sleek architecture that is basically a top-down architecture. No software that's scaffolded around, and what you normally see in PLC and DCS application. It's just this very simple hierarchical architecture. Now, because that architecture is so simple, you can put information pass through it from the bottom up and from the top down. So in MindSight, as I said, a lot of times you need to provide your own power generation, and that's usually provided by generator set, diesel gen sets. And diesel gen sets are very good, but as soon as you overload them, they stall. So you don't want to overload. And so in the mining, there's always energy monitoring. You need to know what energy you're using. And particularly when you start up a heavy piece of equipment, you get that inrush current. So you get a 7 times nominal current that draws, you can hear the gen set, like, you hear that deeper hum, or yeah, you hear that thing cranking when a big piece of equipment starts up. So what happens is, if you have multiple pieces of equipment that you start at the same time, you stall the gen set. So energy consumption is very important. So in the PLC-Easy solution, energy values, energy monitoring is embedded in it. So the energy values from the lowest level is passed up to the top level. So on an equipment, on a control module level, you can have a gas valve, so gas consumption, steam, electricity and water. On a pump, another gas valve, another steam. And these energy values can come from an instrument, for instance, your 4 to 20 milliamp or your Profibus or whatever you're using. And it can be associated with your control module. But if you don't have the money to invest, it can also be a calculation, because in the end, a PLC is a very powerful computer, right? So if you know what your pump curve is, and you know your control value to your pump, so say I'm having my pump running at 43%, you know you can calculate your consumption. So these energy values at a control module level are added up and they're passed to the equipment module level. And the same at the equipment module level, they're added up and passed to your unit level, and from your unit level to your process cell. The operator on a process cell level sees the complete consumption of their plant in water, waste, fuel, gas, electricity, steam. And they are allowed, or they are capable of drilling down up to your lowest consumption level, so to your individual consumption. And with that awareness alone, you will see that your energy consumption will drastically is lowered, because it's like standing in front of a building in the evening. You can clearly see where the light is still on. And the operator can clearly see, like, oh, ooh, I left the steam valve open, right? So that awareness alone will give a lot of energy savings. Now, because it's a fairly simple control scheme, a gas value can, or an energy value can easily be converted into a control condition. So it allows for very quick control energy saving schemes to be implemented in the PLC-Easy solution. Now, going further on the simplified architecture and the ability to pull information through that architecture, one of the other information that is pushed through is operator information. So the operator, by linking these software modules together, the operator is told, okay, you're in step 5 of your sequence, and in this step, your pump is starting, or you've got a problem at step 10. And all that information is automatically pushed through by just linking these software modules together. Now, in conventional system, you would have to program that up. And in PLC-Easy solution, that's automatically done because you link them together through those 8 parameters. Now, going a little bit further on that. So this is really where PLC-Easy is significantly different than other solutions. In conventional solutions, messages are statically configured in your SCADA screen, and then they're being shown when a condition is asserted in your PLC or your DCS. Now, in a PLC-Easy solution, that's different. So the messaging is also passed through that architecture. Now, in conventional solutions, on a condition in your PLC, you show that statically configured message in your SCADA system. And during your design phase, you create an alarm management philosophy, and then you implement an alarm rationale. And that's all done by an engineer, because it's quite a level of expertise that you need to have. So according to that alarm rationale, these messages are grouped together and masked out so you don't get alarm storms. And they're being ordered and grouped and then shown to the right operator. What you see a lot of times is that once a control system is operational, so once a plant is being commissioned and is being taken into operation, a lot of times the alarm management philosophy and the rationale is being neglected. And over time, what you see as changes take place is that the alarming becomes ineffective. And ineffective alarm, per definition, lead to process inefficiencies, so to production losses, and sometimes in worst cases to accidents. Now, in the PLC-Easy solution, the messages are completely done in the PLC and are not statically configured, but they're dynamically generated in runtime. So just like you associate an energy value with a control module and with the equipment module, you associate a message in your PLC with your control module, with your equipment module, with your unit, and with your process cell. And because you put all these software modules together in the architecture of your plant, of your control philosophy, all these messages are automatically in that same architecture in your PLC. And every software module has that universal control algorithm in it that contains that alarm management rationale. So all these software modules, they alarm manage actively for you. So all these messages are automatically structured and ordered and masked out. So if you have one condition that leads to multiple alarms, it will not show you that all that alarm list. It will only show you the root cause. So that alarm management algorithm is actively working as you are in operation. And if you do changes, it's you don't need to change anything because it's embedded in here. You just add your messages to it. Now, all what you need to do on the SCADA side is you instantiate your object. So you create your object and you link it to your PLC and you place it on your graphic, and that's it. So all this work that you normally have is now reduced to basically instantiating and placing it on your graphic. Now this alarm management is significantly different. And there's no other system that I know of that has. And that simplified alarm PLC alarm managed structure allows for all sorts of other information. So basically hardware performance, hardware diagnostic signals. Sorry, I take one step back. In a conventional system, you would see an alarm message like this. There's something wrong with valve 3. Now, the operator now has to leave their post or they have to call somebody to investigate. Now, in a PLC-Easy solution, alarm message would look something like this. It always starts with your root cause. So in this case, the equipment that caused the problem is a low level switch and the state of that device is off. Now, that caused a protection interlock, the consequence, and that affected, now that's the S88 pathway, so the location, pasteurizer 2, control valve 1401, and the state of that device, that control valve, is tripped. So the operator sees in one sentence the root cause, the consequence, the affected device, the state of the affected device, and the location of the affected device. On top of that, the operator gets a timestamp that it does not originate from the SCADA system, but is a snapshot of the PLC clock. So as soon as that the PLC sees a change of state, it takes a snapshot and affixes that to your message. So in conventional systems, this timestamp comes from the SCADA system, and the SCADA system has at best a read cycle of 1 second, but most of the time slightly longer. So if you have rapidly cascading events that happen within that read cycle of the SCADA system, they all get the same timestamp, and then you need to do a root cause analysis. Well, in the PLC-Easy, if you have rapidly cascading event, for every event, a new snapshot of the clock is being taken and is affixed to that message. So if you have multiple issues, multiple alarms, the operator can clearly see by just looking at the timestamp, like this is your root cause, right? So you don't need to do a root cause analysis, which can be quite time consuming. So empowerment is one of the key words that defines the PLC-Easy solution. Now, with hardware diagnostics can be added to a control module. So in conventional system, a hardware fault, you need to program that in your control modules, your equipment modules, and then you need to program the visualization on your SCADA side. Now, in the PLC-Easy solution, you don't need to do anything. You just need to take the hardware diagnostic signal and you link it with your control module. And for instance, that can be from a motor starter, a variable speed drive, or that can be from an Ethernet switch, right? It can be from anything. It can be from an I/O card. It can be from a vendor's kit that has their own PLC, right? From a completely different PLC. So you can add these hardware diagnostics, you can link them to your software blocks in your functionality. Now, this is super flexible. The great thing about it is if I change out my VFD for a new VFD, the only thing that I need to do is I swap out my hardware diagnostics, but my functionality remains exactly the same because a pump is a pump, right? The way you power that pump is not of effect of your functionality. Now, in conventional systems, if you do this change, it cascades into your control logic and into your SCADA. And with this, it just remains at that hardware level. Now, the other advantage is that you can combine hardware diagnostics. For instance, the previous VFD, that was a 4 to 20 milliamp VFD, and I'm replacing that by a VFD that is connected through Ethernet, right? So if the Ethernet switch has an issue, that will affect the VFD, and that will affect the control functionality, right? So I can take the hardware diagnostics of the Ethernet switch and even the port of the Ethernet switch, and I can just combine it with the hardware diagnostics of my other device. So if there would be a problem with the Ethernet switch, the operator would be notified automatically, hey, there's an issue with your switch that affects my motor drive and that affects my pump functionality, I don't know, pump 11. And the only thing I do is I just link these software modules together. I don't need the program. Now, that effectively gives me in my code a separation between my functionality part in my software and the software that drives my hardware and that collects information from my hardware. And that gives a significant advantage during your development. So normally if you start developing a control system, you need to have all the electrical design finished. And in this case, you can actually, with PLC-Easy, because you got that separation, you can start with your functionality and you can do that concurrently with your design or before your design of your electrical system. And you can add these hardware diagnostics at a later stage. Or if you are operational, you can basically swap out a piece of hardware. If you have an outdated piece of hardware, you need to upgrade it, you can just swap them out and your functionality remains unaffected. Now, for the pharmaceutical industry, that's a big advantage because a lot of times you have to validate the software that controls your machines. And it is quite a lot of work to change it to get it revalidated. Now, with this, that validation is only on the hardware diagnostic side and not on your functionality. So with that, I'll quickly go to a demonstration. Let me see how we are on time. Okay, I got 10 more minutes. So what does it look like? So at the moment, the PLC-Easy solution is available on Schneider, and I got some reasons for that. And here was a pilot that I did for a dairy factory in the Netherlands, which is a pasteurizer. So all these function blocks, all these symbols that you see, a pump, an analog, a valve, those are individual software modules like those Lego bricks, and you're just linking them together. Now, for instance, I've got two devices here that are grouped together. So I've got a seal water valve and I got a pump. And the seal water valve doesn't really have any bearing on the process, right? If that valve provides water to the pump, it doesn't change my pasteurization, right? It has no influence on my process, but it does have a big significance for my pump, right? Without the seal water valve, my bearing starts to crud up with product, and in the end, my pump will die. So when I want to run my pump, the pump needs to open the valve. So in this case, in a PLC-Easy, in a Lego brick representation, I've got a valve software module and I got a pump software module, and I click that pump on top of my valve through those 8 parameters. And all these information and commands are now basically coming from the pump. Now, I just issued a manual command to my valve, and if my pump want to control my valve, it couldn't do it because it's in manual mode, right? The pump cannot take control of it. So the valve reports that back to the pump, and it says now here, look, your slave is not ready because it's in manual mode. I can't control this. Now, in turn, all these software modules are part of the pasteurizer. So the pasteurizer is that gray Lego brick in that representation, that Lego brick representation. So if I open that one up, the pump is basically clicked underneath that pasteurization block. So the information travels up through my hierarchy from my valve to my pump to my pasteurizer. And so the operator here is told, look, you cannot control this pasteurizer because valve 1303 is causing you an error because it's in manual mode, right? So that information travels up in that hierarchy, and I haven't programmed anything yet. I just linked it together. Now, information travels up, commands travel down. So for instance, if I issue this pasteurizer to go out for maintenance. I'm taking it out for maintenance completely, and I'm issuing the command here. Then all the slaves, everything that's underneath this particular equipment module will follow in that out to maintenance. So here I see that everything now is out to maintenance, and I don't have to program anything. Being cognizant of the time, I'll take this back into operation again, and I'm going to issue an automatic command to all my subcomponents, all my slaves, and now we'll see that everything goes to automatic. And now I'm going to start my pasteurizer. Now, what you'll see is here that the operator will be informed every step of the way. It's in step 1. My valve is opening. And normally you need to program this up. You don't need to program. You just link it together. Now, from step 1, it goes to step 7. And valve 1110 is opening. And part of that same step, my pump is starting. So every step of the way, the operator is notified of what's happening. And so the operator can see that quite clearly what's happening. Now, for instance, if I would cause a big problem, and there's a lot of information here that's happening, and pretty much the operator doesn't really need to know about it. But if there's something significantly happen, you want to have your operator be aware of that. So I'm going to issue a problem now. I'm going to lower the level of this heating media tank. And basically, if there's not enough heating fluid here, then I got to stop my my steam to this, because otherwise it can damage my heat exchanger. Now, I'm causing a major problem. Now, my operator is notified straight away. My pasteurizer is automatically stopped. You see here it's going through a stop sequence. You see that it's counting down in steps. What's the problem? Well, your control valve is causing a problem. It's tripped. Okay. So I click on that link button. It takes me to the control valve. I notice that I don't have any operator buttons anymore except for a reset and an out to maintenance. And what is my problem? Well, your problem is that you got a protection interlock, and that's caused by your level switch that has turned off. Now, that information I see here as well. So some alarms don't travel up. This alarm needs to go to the top because it stops my process. My operator needs to know straight away. So here I see that again, slightly different. I see it that it starts with the root cause. So my device that caused the problem and the state of that device, then the consequence, and then the affected device with an accurate timestamp here. Now you can see here it's at 11:41. And if I'm looking at my SCADA clock, you see here on my SCADA, it is the 2nd of September at 5 o'clock. And so you can clearly see this timestamp does not originate from the SCADA. It originates straight away out of my PLC. I'm going to cause another problem. And a quick little side jump. These messages that you just saw, the control valve, the level switch has turned off. I can change these strings. I can change these messages on the fly in runtime. So instead of off, I can say media low. And I enter that, and I close that off. So if I quickly reset my valve, it's back, and I'm going to cause the same problem again. And now it should say, instead of off, it should say media low. So there it is, media low. So my alarm message has been automatically, or in runtime, has been changed. Now, compared to conventional systems, that would be a statically configured message. You would need to have somebody with a lot of expertise changing this. With this, I can just change it from the SCADA system, and I don't need to be an expert. Empowerment. Now, that was very quickly a very short demonstration. I'll quickly go back to my slideshow. So the big problem that I find in the industry is that human nature, that's the biggest issue that I see. So, and the cartoon says it all. The most common phrase that I hear is, "We always do it this way," right? And that is a very hard one to overcome. But the PLC-Easy solution is a truly innovative solution. So there's nothing new. It makes use of hardware that everybody is using at the moment. It's using the same program environment that everybody is using, but it's using an architecture that's different, that is actually simpler of what people are now doing. But the human nature is the hardest part. I quickly want to highlight why I chose for Schneider the M580. It's got a lot of advantages, but the biggest advantage that it has is that it has Ethernet, secure Ethernet embedded in their hardware, in their PLC. So an analogy is, hey, you remember the telephone, you remember the old trusted computer, a compass, a camera, a Walkman, and when you put it all together, Steve Jobs gave us the smartphone. Now, what Schneider did, they have a PLC. You combine that with an Ethernet switch, with serial communications, with routers, with wireless telemetry, with a firewall, and you put them together, and basically you've got yourself a cyber secure PLC. Now, the great thing about that PLC is that you can take information that is not process control related, so IoT information, and you can pull that out of your PLC, out of your field, without going through your controls network. So it combines your OT infrastructure with your IT infrastructure. Now, and I'm sure if you're in this field that IT and OT, they always are fighting with one another. And if you look at DCSs, and this is the big advantage of DCS, is that a DCS can take information that is not process control related. So that could be, how many hours did my pump run? Or is there any wear and tear? Is there vibration on my motor? Is there heat on my motor? And that really doesn't have any bearing on the process, but it surely tells me something about the lifespan that I have left in that device, if it's about to stop and give me downtime, production stop that I did not plan. So in a DCS, they can program that up for you as long as you use their field devices. And the problem with the DCS is that they always charge about 4 times the price that you have for a generic one. So if you would want to have something else here, you would need to program that information in your control software and in your SCADA software. Now, with the PLC-Easy solution, if you would change out something here at your field level, your control software will remain the same, and your historian and your HMI side will remain the same. The great thing about the PLC from Schneider is that due to the firewalling, VLANing, and time-sensitive network protocol, you can take non-process related information, so IoT information, you can pull that out of that field layer, completely bypassing your controls layer, and put that in the edge or into the cloud, completely cyber secure. Now, that, in my opinion, is a very smart concept, because you don't get that OPC and IT infrastructure right in your controls, because cybersecurity is there's a lot of things to say about that. So a clever solution. Now, there's a couple of testimonies by Schneider and Brunel in Europe. One thing is that they're quite taken in by the solution, but the other thing that they're saying is that this software is written exactly the same way as Schneider does themselves. So it's not written in the IEC 61131, but it's written in C language. And the Schneider company provides a software tool, and they call it the EFB toolkit, which allows you to program in C and import that in an IEC 61131 environment in their EcoStruxure or in their Unity Pro. And so the big advantage of that is that it's much faster. And the great thing is when Schneider upgrades their hardware or their programming environment, this remains supported. So it's supported indefinitely. Now, to conclude the presentation and demonstration, so the benefits of the solution that's completely based on an algorithm is that your software is reduced by at least 30% and your complexity by at least 50%. And that reduction, you see that in your downtime. That affects your unplanned downtime, higher reliability. Because you're using the same algorithm over and over and over and over again, you get very consistent software quality, very predictable. You've got infinite redundancy. That's only limited by your hardware, whatever that PLC can take. How much memory do you have in there? How much software do you running in there? It follows the S88 and S106 standard very closely, and it's also got a high level of compliancy with the IEC 61499. And I can elaborate that later if there's time for that. It's got integrated exception handling and hardware diagnostics. It's got integrated alarm management, which greatly reduces your SCADA development. And it's got fully integrated energy monitoring. And best of all, it's much simpler than conventional systems such as Siemens PCS7 or Emerson Delta V or ABB 800XA. In short, it's simply amazing automation. And with that, I'd like to hand it back to you, Vladimir, for questions or further elaborations.
Okay, Martin, thank you a lot for a great talk. So, dear colleagues, if we have the time for your questions, you may raise your hand or maybe some just saying to use your microphone. So, dear Martin, I have a questions about your presentation. Firstly, I'm very glad to hear from you the thoughts I also have about conservative nature of the fields, about problem of emergency event processing, about complexity and so on. So my questions is about you speak about messaging, but what do you think about automated processing of the emergency event? So, for example, if we want to describe functionality when some valve, for example, broken, what do you think? Are there any solution for this or some conventional strategy?
Yeah. So there's two answers to that. So I briefly showed you a really bad fault. Had that media, that heating media that lowered, that kind of stopped the whole machine. I can also show you a fault that will stop the machine to an extent, but not completely. It will remain running to the point where you've configured it to run. And if that condition improves on itself or you've got an operator interaction, then it will continue again. So that's one of the answer. The other thing that I found is that, especially in energy, is that you've got a safety PLC that in case my software in my regular PLC kind of malfunctions, the safety PLC kicks in and does a safe shutdown. Now, with the PLC-Easy solution, I can also create a safe shutdown in case if I use the abort button, that it bypasses the normal stop sequence, but it does a completely different stop sequence. So because you're much simpler, the software is less susceptible to hanging. But if it does hang, you can basically hit the abort. It can be then completely dead, or you can do a safety stop. For instance, in a agglomeration tower or a drying tower, for in the dairy where you put in fluid in the top and you have a really hot tower, and by the time it's at the bottom, you get powder. There's a lot of energy in that inertia, and if you would stop that tower like completely dead in its track, then that powder has a good chance to blow, to explode. So in that case, you need to have an emergency shutdown that will open a particular valve or open a particular vent and keep a fan going, so keep that cool air in. So the PLC-Easy solution can do that without a safety PLC. So from a software point of view, you can build in a higher level of safety just on the software. And hardware, of course, it cannot. If the PLC seizes for whatever reason, that cannot be accommodated with software, of course.
Yes, but I speak mostly about hardware fault. I mean devices, kind of valves, pump, and so on. We think that PLC is okay every time, and I see two strategy that is to lead the whole system, control system, and plan to safety state one path to say some safety state, and another to use some kind of redundancy.
Yep.
I think two pumps and so on. If one pump is broken, and we can switch to additional pumps. And so, okay. But I have a feeling that such kind of operations now mostly doing in manual mode by operator. Is it true? From practice point of view, can you provide some good example for systems that process emergency events in automated mode?
Yeah. So one of the applications that I did was for a data center, and so data centers have cooling units that provide cold air to the server rooms where all the server computers are standing, and usually the smaller ones that they have 4 cooling units, and depending on the weather outside, if it's really warm, they start an additional, and so they always have capacity. They always for the warmest condition, they always have 1 cooler extra. So you want to stage those. You want to kind of have wear and tear on those cooling units equally. So in this solution with the redundancy, you can put them in redundant. If one fails, the other one kicks in straight away. And you can also stage them. And you can say, okay, this time I'm running this one first. If the temperature outside becomes higher, then I'm going to start my second one. And I've got my 2 other ones in a duty standby. If any of these 2 fail, I kick in number 3. And if number 3 is not available, I kick in number 4. So from an high availability standpoint, that's completely standardized within the solution, and you just link these cooling modules together, and you tell it you're number 1, you're number 2, you're number 3, you're number 4, and it will balance itself out according to that prioritization.
Okay, thank you. And the next my question is, what language do you use? I mean, for PLC, what PLC language do you prefer from IC6, 1131?
Yeah, so PLC and DCS traditionally use IEC 61131, but this is written in C. And the Schneider environment allows you to import a C source that's written in C. And I think that what they're using is, if you program in the IEC 61131 language, it converts it underneath the hood to a C kind of language. I'm not sure what the compiler is, but they they also support the C language, because a lot of times it's got Intel Celeron processors running in those PLCs. It's just a simplified PC, basically.
Okay, your point is quite understandable. In the case of complex functionality, most of the programmers prefer to use just plain C to use it.
Yeah.
Okay.
So the modules are written in C, and the modules are important in the Unity Pro or the EcoStruxure environment, which is an IEC 61131 environment. So you literally use function blocks to link together, and it's very much like
do
those.
you use FBD, function block diagram?
Yep.
Yes, as
Yep.
the part.
And otherwise,
The
I can.
structurization and what mechanism structure to provide provide encapsulation, for example, for this. Yes.
So this is basically what you're using, and I skipped over this for the reason of time, but the program that you saw running is 5 sheets of code. It's basically this, and so most of those sheets of code are completely standard logic. So these are my analog and my digitals. So I've got 16 analogs and I've got a handful of digitals. So these are all standard software modules. There's no unique programming. And I've got 6 PID loops, and I've got some communication, and I've got my controls. Now, the control that you just saw running is this sheet. And this sheet is about 80% of standard logic software modules. And only this part is unique software. And that's providing the routing. And I didn't demonstrate the routing, but the routing is basically AND and OR gates. So this is really your standard IEC 61499 function block programming. The PLC-Easy blocks that you just saw working, so the Lego bricks are these. And basically what you're seeing here is the sequence. And the sequence is going from the left to the right. And now normally you have a lot of sequencing software or an SFC, so a graphical way of programming a sequence in a DCS or a PLC environment. But these are just the function blocks. So here's a valve, and the valve is step 1 in the sequence, and step 2 is another valve. And basically what you're seeing is those 8 parameters that I was talking about are these. So there's 4 interlocks, a step number, a master, and 2 duty standby pins. And that's basically every time you use those same 8 parameters to connect. And for instance here, I have a close interlock, which is an OR gate if one of the valves is closed, or I have a route that takes me to my storage, or I got another valve that's opened. Well, then I got a close interlock. So that's basically your 101 AND and OR gate programming in PLCs. And so the sequence you see here from the left to the right, going from step 1 to step 12. And that's pretty much my program. And compared to conventional systems, that's quite simple. And it's function block programming, IEC 61131.
Yes, I see it's kind of data flow strategy, data flow function block diagram.
Yes.
We connect data between the function blocks, and it's okay. What is your approach to check malfunction of for example, for the valve? Mostly control program I see, it's just don't worry about it. Just they written in the assuming that if you put some control signal to valve, for example, the valve must be shelved open or close and so on. But in the practice, we have, in the case of malfunction, for example, we put the signal valve on, put the signals to the valve is on, but valve is still closed and so on. It's malfunction. What is your strategy to check this kind of malfunction?
Okay, so pretty much any condition that can occur in a device. So for instance, a pump can be failing to start. And so that could be there could be the contact that could be welded together through heat, through use. So fail to start, fail to stop. It could be that when you start a pump and stop, start and stop, you constantly get that inrush current, and that pump gets hot. You need to cool it down. So these states of a pump and of a valve fails to open or fails to close, or there's something interlocking it. Those standard messages are embedded in it. But when you have a condition that stops it from opening or from closing, that is really specific to your application. And for that, I'm using that message block, that unique feature. And that message block I link to the valve block. And if that condition is not valid, for instance, an open interlock, it takes that message block, it pulls that information into the valve block and pushes it up into the SCADA. So the operator always knows, like, okay, this is the condition that stops me from actuating this valve.
But you speak about processing of the malfunction, but what the low level? For example, which way can you define that valve is broken? What is your strategy? What is your function? What is your algorithm to check that valve is broken?
Yeah. So there's
valve is broken because I can speak about us. We constantly use timeout control. We know that in specification of the valve, we can reach that valve must be open within, for example, 1 second after control signal, and so on.
Right.
What do you do in this case to check malfunction?
So, for instance, if I'm opening this valve here, control valve, so you can configure this. So,
yes, I see. Close. Yes, close file time. Yes. Open
yep.
File. Yes.
So I can tell it here. Look, if you didn't receive your field feedback, your open switch in this particular time, you tell the operator, look, you got to fail to open. And you could also put in a warning time. You can say, like, if at some point, depending on the material that flows through your valve, the valve slowly starts to corrode. And in some processes, so for instance, in the dairy, when you have like sugary substance going through your valve, that valve starts to get corroded down. And you can clearly see that in the time it takes to open and to close. So you can put up a time where you say here, if it doesn't reach that open status within this particular time, give a warning, because your valve is still working, but it's on its way to become corroded. And so those common characteristics, those common faults that you find in equipment, I've programmed that up in here. So for instance, here it's your move time, it's your fail to open, fail to close, your step timeout. If it's in a step and your condition doesn't occur, then you can say, okay, timeout. The sequence has to stop. My machine has to shut down because this particular condition did not happen in that particular time. And this can also be configured, for instance, for a pump. If I take a pump here, I have the amount of start limits in a particular start limit time. So, for instance, if I start and stop this pump within 2 minutes, then I got to shut this pump down and we're going to go into a cool down. Now, how much is my cool down then? I can define that here. Well, that's 5 minutes. So I protect the valve from becoming damaged. Sorry, the pump from becoming damaged for the motor windings to get too hot, so your insulation doesn't become brittle. So you can, a lot of these standard features that can damage a valve, or that can tell the operator something about the functionality of the health of the device, is embedded in the control logic.
Okay, thank you. Yeah, I see the answer to my questions. I know there is a lot of participants, at least three participants from verification field of the control algorithm. So I maybe ask the question. Questions about problem of the correctness of the program and the program correction problem, because some malfunction in functionality may be caused by programming. Do you have some solutions for this kind of errors?
Yeah. So every function block it's got the algorithm in it, and that algorithm basically really takes care of when to open a valve, when to close the valve, right? That part is really, it's I would say bulletproof, right? It's really robust. It's what you hook up to those 8 parameters that will trigger those internal functionalities. And if you don't hook up those 8 parameters through an AND and OR gate correctly, you will see it will not properly work. So you will find those programming errors very early in the development process. And because every condition you connect the message block to it, you will straight away see on your SCADA side, hey, your valve is interlocked because of this reason. Hey, your level switch is off, and that affects this particular valve or this particular pump. So the troubleshooting is not so much in the code itself traditionally, but you can clearly see your programming mistakes in your SCADA side, because it just doesn't progress the way you want to progress it, and it will tell you why. So program errors can still occur, but they're much likely to be coming up earlier and to be more visible.
Yes, but that's a lot of questions. 2 questions. One question about robustness, correctness of the function block that you specify in C. It's one question. It's that you just stated it is robustness, but it's the situation is you believe to yourself. But when you deal with third-party libraries, for example, we cannot believe. For example, from Russian program, yes, that some bugs and so on can be. So it's one question about robustness, correctness of the function block that is written in C. It's as I understand you say that it can be proved by dynamic verification, by testing. Yeah, it can be proved. You can run it and look at the behavior of the function block.
Yeah.
Yes, but it's okay. But the second question is about program errors on the level of configuration. When we configure of this function block, we also can make some stupid errors. For example, process needs valve need to be open, but programmer may say its valve is closed. For example, zero and on and off, such kind of logical errors. Are there any technique or maybe approach to prove these errors? And also, what I mean that such kind of errors, it's very dangerous to find within control software is running on the real plant. It's, for example, plant is nuclear electric station. It's very dangerous to find it when the software running. Do you have some approach method to catch such kind of errors on the earlier stage of programming?
Yeah. So I think I understand the question. So you said you had two questions. I want to go back to question number one. So this solution has a lot of attention from Schneider Electric. And because I'm using their hardware and their software in a different way. And they're very interested, and there's talk to make this a Schneider product. So this was evaluated by Schneider Electric, these function blocks and the algorithm, over a period of about 18 months on quite extensive. And that's why they wrote that statement that it was programmed the way Schneider would program it. So there's a high level of confidence by Schneider in this. The second is
oh, excuse me, about the first questions. Maybe you know that do they use, for example, not only testing method, but for example, so-called formal method of verification of the function block? Maybe do you know about model checking, or maybe deductive verification? So mathematical method to prove the correctness of the algorithm. Maybe do you know about Schneider inside information?
Yeah, no, I'm not familiar with that type of validation. So what I did do, so I wrote a patent document for this. And so in the patent document, you write basically what it's supposed to do and when, and it's tested against that. On the programming side, the way you use it, so because it's the functionality within the algorithm cannot be changed. So you can really predict like how it's going to react. It will react the same way over and over and over again. And so that really the error you take out of the function block and you really put it outside of the function block on how you use those 8 parameters. And that type of fault, so that's basically AND and OR gates on your interlocks. And those interlocks you make visible on your HMI. And so when you validate your design, so let me share my screen again, share. So here I am. So here we go. So the software is basically created from this design document. And in that piece of software where I showed all the function block going from the left to the right, that sequence, you see that here from the top to the bottom. And so first what you do is you design your software and basically you say, okay, in step 1, I need to open my valve 1101. And that's the description, it's the short circuit. Now, do I have a protection? No, I don't have a protection for this valve, not necessarily. Is it part of a route? Yes, it's part of a route. And so you can test against, like, if my route is active, okay, this valve is opening. So that's a test criteria here. When can it run or when can it open? Well, if my tank level is not high, and that signal is provided by high level switch 1101. Is there a start condition? No, there's no start condition. It's only a run condition. When can it stop or close? Well, if my pump 1101 is stopped, and if my pump 1201 is stopped, and my pump 1301 is stopped. So you can, here on the right-hand side, you'll see here the test. So you can basically, for every condition, you start and you stop, you test against, you design what you described here. And so that's basically how you catch yourself on, did I configure the function blocks correctly? So that's how you I wouldn't say validate, but how you check your functionality against your software, if that makes sense.
Yes, yes. Thank you. How about second question? I see it looks like kind of sequential function chart.
Yeah.
Yes, sequential SFC.
Yeah, SFC. Yeah, SFC. Correct.
Okay, thank you. What about some kind of techniques based on the digital twin concept? Do you use some kind of such approach when we use some computer model instead of the plant?
Yeah, so at the moment what you're seeing is basically simulation. So every function block has a simulation in it, and that basically means if the function block is being activated and it energizes the field, the simulation say, okay, I energize the field, so I loop it back to my input that's saying, okay, my field is running. So the simulation part takes care of that feedback loop, and the functionality that you see running doesn't know if there's a field connected to it or if it was a simulation. So it's a very true representation of what you're going to get in the field. And one of the things that I like, and that's what I'm talking with Schneider about, is IEC 61499, which is basically a distribution of your control to field devices. Now, at the moment, every function block of the library is based on the same algorithm, and that algorithm is 300 lines of code. It's very slim. Now, at the moment, that algorithm is running in the PLC, but a motor starter has the capability of running this, right? So you could take this out of the PLC and you make that run in the motor starter. So now I got a self-controlling motor starter, and that I can connect through Ethernet with those 8 parameters to another motor starter. And now I got autonomous devices that kind of control by interconnection. So if you would take a motor starter, for instance, an E3 Plus from Allen Bradley, or a Simo code from Siemens, or a T60 from Schneider, a small motor starter, which is basically a smart relay, and you would actuate a valve on that, you could run that in that valve smart. So now all of a sudden I've got pumps and I got valves that are smart. So the whole thing about IEC 61499 is to create a new way of programming and to distribute. So Schneider is interested in the solution from that objective as well, because it could facilitate that.
Yeah. Thanks a lot. And a lot of questions, but it's too late. For example, maybe, dear colleagues, do you have some questions? Okay. My question is about distributed control solution. What it's mean for me that there is a lot of PLCs in the field, several PLCs in the field, and there is such a problem arised, so-called device-centric paradigm versus application-centric paradigm. As I mean, that as a programmer, I am very, it's very comfortable for me to describe functionality as in whole, when I don't don't aware about how many PLCs is on the field. And as I know, some problem, there is a problem in the IEC 61131.3 standard that is provide, encourage the user to the programmer to use so-called device-centric paradigm when they describe, they have to divide functionality on the PLCs and describe software for each PLC separately. What it's very interesting your opinion on this issue.
So I hear a lot. So my background is partly in Emerson Delta V, which is a true DCS, and what I hear there is a little bit what reminds me of Emerson Delta V. You got a piece of functionality and you say, I assign it to this controller, and the tags that connect it to that particular call it PLC controller and the field is managed for you in that engineering environment. You don't really have to say it's that PLC and it's that address on that particular I/O card. It does it for you. So I see that in DCSs more than in PLCs. PLCs still have that little bit of a legacy. It's one particular device, and you've got your I/O, and your I/O is based on I/O cards, so you need to assign the addresses. And I can see that that requires the Schneiders, the Siemens, and the Emersons of this world to change that. I couldn't really change that with this, but what I could do with this is what I said before, is that in my opinion, this doesn't necessarily need to run in a PLC. It could run in a device if a Schneider or another big company would work with me. You could create autonomous field devices, and that of course opens up a whole new can of worms, a whole new set of challenges. So how are you going to manage that, and how are you going to say this goes to this particular pump and this goes to this particular valve? So yeah, very interested in brainstorming about it, but it's out of my area of influence.
Yes. Yes, I see. Well, that is looks like a centralized solution, not distributed solution. But when we, for example, when we open modern vehicle car, we can see maybe 100 of microcontrollers inside that intercommunicate with each other. And as I see, as to my understanding, it's a problem of the wiring. It's more simple to connect it to the microcontrollers by wire, by single or maybe two wires, and that's all. In centralized solution, there is a problem too. But maybe in the solution you speak about, it's not the problem, because PLC, as I understand PLC, you propose that PLC can be reduced to just some I/O card, remote input-output card. Yes, and centralized solution of the.
Yeah, correct. In a lot of motor starters, particularly VFDs, they always have an analog input, usually two. They always have a couple of digital inputs, some digital outputs. So the motor starters in itself at the moment are mini PLCs, if you like, and so you could create true distribution, and they're already Ethernet enabled. So I think if people would put their minds to it, and I think this could facilitate it, yeah, you could look at true distribution by autonomous devices, and I'd be really keen to be part of that journey. Yeah.
But now your solution is assumes that control code is executed on the several PLCs.
Yeah.
Is it?
Yeah, could be.
Yes.
Depends on on the size of your plant, and I think it's very wise to have a level of basically creating little self-containing control entities. So, for instance, if you have a dairy process and you've got, if I'm talking milk, you got a milk intake, and you control the pumps and the particular tanks and the filtration, and that's part of your milk intake, you assign that one PLC. And so if you have maintenance to another part of your plant, your milk intake can keep on running, and you don't touch it. So from a very strategic point of view, I think it's wise to use multiple PLCs, and where currently PLCs are so powerful that you could run a quite substantial plant on a single PLC. It will support 1500 I/O, no problem. But from a strategic point of view, would you want to have that? It's a PLC from Schneider is 8,000 euros. That's your highest end M580. For 8,000 euros, I wouldn't take the risk of. I'd rather spend an extra 8,000, and I know, like, okay, I've got compartments. My production can keep on running, and another part of my production I can have. I can take the power off, and I can maintain it. And so that's worth that 8,000 euro, like, over and over and over again. So I think a technical point of view, it's becoming strategic at that point.
Okay, Martin, I see that there is middle night in the Cleveland, so unfortunately it's time to make some conclusion of our discussion. Firstly, I would like to say that I am very glad that you agreed to make this great talk to us and discuss some questions. And also, I personally very glad to hear from you. You sound the problem that I also see that it's a very important problem. For example, problem for emergency event processing, about complexity of control software, that it must be very simple, simplified, that current control software is very complex, and so it's very complex. Complexity means that it has problem with robustness and problem with correctness, and so on and so on. It's very glad to hear from you these thoughts that we mostly deal with. So many thanks to you for your great talk, and I think we will still in touch, and maybe discuss some maybe interesting issue that is acute in this field, in the field of control software. Thank you a lot.
Thank you very much from my side. And they say find your problem and you find your greatness. So bring me your problems, and I'm happy to have a look at it.
Thank you a lot.
Thanks. Have a good day.